Let's welcome our next speaker of the session, Arvind Kumar from IBM, who is going to give a talk on heterogeneous integration for the future of AI. Dr. Arvind Kumar is a principal research staff member at the IBM Thomas J. Watson Research Center, where he manages a team focusing on next generation AI hardware, including heterogeneous integration. He has presented several invited talks and served as a panelist and short course instructor in this area at major conferences. He holds over 50 patents and is an IBM master inventor. Dr. Kumar earned SB, SM, and PhD degrees in electrical engineering and computer science, all from MIT, and held an SRC graduate fellowship during his doctoral studies. Welcome.
Perfect. Okay. So thank you very much. I'd like to start off just by thanking the organizers for this invitation, for the opportunity to be here. And I would reiterate the message. I hope everybody got a cup of coffee. We'll go through the talk. I have 30 minutes or a little bit less with questions, or 30 minutes? Perfect. 30 minutes total. Okay, excellent. So why don't we get started? So I think there was probably an older title on the original agenda. So I'm actually here to talk about heterogeneous integration for the future of AI and why HI is so really critically important for AI in order to meet all of the big demands that AI is imposing upon our computing systems. Okay, so this is an outline. I'll start by giving some introductory points about the growth of AI. And what's happened to model sizes and the demands that those are placing upon compute. What are the real requirements for AI? And then I'll switch gears a little bit and talk about heterogeneous integration, or HI, where we are today and where we think we need to be in the future. And then I'd like to combine both of these and put a roadmap of the path forward, how we can really leverage the advances in HI to meet the demands of AI. So I think everybody knows AI is really here. It's everywhere. It's exploding. It's really influencing many, many different aspects of our lives. And there's so many applications of it. And the real reason why we're so interested in AI, if you look at this chart, it shows the exponential growth in what's known as unstructured data. So this is not the kind of columnized data that really computers were very good at in the past. This is unstructured data that may come from social media. It comes from IoT. It comes from many different sources, but it's not something that's easily processed by the algorithms of the past, where computers really look like big calculators. And that's why we need AI algorithms to be a little bit more thinking like humans do in terms of processing this data. And that's led to a literal explosion in AI and its applications. So what you saw in the previous chart was really looking at kind of specialized AI, some various applications. It's really good at telling a cat from a dog, or it's good in your autonomous vehicle, or it has some other particular application, maybe it's speech recognition. And that's kind of what you see at the left side of this chart. But what we're doing is we're really transitioning from narrow AI, which focuses on single tasks and superhuman accuracy and speed for certain tasks, to a much broader aspect of AI, which is broad AI. And there, we'd like AI to be able to do things a little bit more like humans do, where they can look at multiple tasks, multi-domain, multimodal, and that might involve a more distributed platform for the AI. And the other big thing about AI that we'd like to transition to is actually being able to understand it. So many times it even gives us the right answer, it gives us superhuman accuracy, but we don't understand why. And that is a big bottleneck. And then on the right side of this chart is probably where we might be a couple of decades from now, or maybe even 1 decade from now, which is much more general AI. So what is this really doing to the compute requirements and the model requirements? So this is a very good plot that shows a number of these AI networks and the parameter count. So what this is I'll talk a little bit more in a minute about what, how an AI network looks. So don't feel that if you don't understand this chart, I'll certainly get there to explain a little bit better. But the y-axis is a log scale of the parameter count. So that's how many parameters are needed in an AI model. And what you see in the lower left corner is a lot of these blue dots, which were for more of these specialized types of AI networks. But what's happening these days is more along the trend line of the red, which is generalized foundation models, which are large AI models that can be adapted to a wide range of downstream tasks, meaning that you can kind of train them once in a very general sense, the way we as humans are trained. We were able to do a number of tasks, or we can train ourselves to do a more specialized tasks, but we have a large body of general knowledge that enables us to quickly adapt and then pick up a new task along the way. But what you also notice is that the parameter count for these models is truly exploding. So this is going on a completely different trend line from what has been seen in the past. And it's even getting larger and larger with models such as GPT-3 and G-Shard, which you see in the upper right corner of this plot, approaching the trillion parameter count. The green line in this plot is looking at the memory capacity for various GPUs. And you can see now that the parameter count is quickly exceeding the memory capacity of the GPUs. Now, what does this do to the compute? So the y-axis here is the number of petaflops that is needed to train one of these models. And I'll get into what training versus inference is in a minute if that's not clear. But just for now, think of it as a metric to say how hard it is to actually train and create one of these AI models. And again, you see the blue dots, they're kind of scattered. These were some of the more specialized models. And now as we move into these more general foundation models, we're now moving along this red trend line. And you can see that the requirements for compute are growing tremendously as we create larger and larger models and therefore need to train them as well. Okay, so let me talk a little bit more now in detail about what these AI requirements are. And I'll start with the compute and then transition into the memory requirements, particularly the bandwidth and the capacity, and then also about the connectivity requirements when we have a distributed system of AI processors. So this is like a neural network. So what you can see here is the neural network consists of multiple layers of several nodes apiece. Those are the circles. And these nodes are interconnected with each other by weights, which are stored in the form of a weight matrix. So there's a weight matrix which connects each layer to the next layer. And that's what you see in this picture. So if you wanted to train this, you have all of these weight parameters that need to be specified. And the way that that's done is usually you take a large body of data and then you just run it through the system. So you might start with an initial guess for what those weight parameters are. And you take say a picture of a cat or a dog, you run it through, you ask yourself, well, what did I get at the end? And then you compare it to the right answer or the ground truth. So if it's a cat, you see did it predict a cat? And if so, you kind of reward it. And if it's a dog, you say, well, you didn't get the answer right. So what we're going to have to do is correct those weights. And that's done through a process known as backpropagation. So it just goes backwards through the network and then makes a correction to those weights in the direction of getting the right answer. And then at some point you say, okay, I got enough accuracy and my model is trained, and then I can actually deploy it. So that's training. And then when I want to deploy it, sometimes I'll have a large bank of data and sometimes I won't. For example, in an autonomous vehicle, you're just quickly trying to tell whether there's a pedestrian in front of you. So you have only one thing you want to pass quickly through the system, and latency is very important in that case. But there you're only doing a forward pass and just trying to predict an answer. So the use cases for training versus inference are quite different. As we were just talking about, the inference or deployment might be in an automobile, but the training may have taken place in the cloud on a very large system of GPUs. But the math that's behind these two things is very similar. And in fact, what you can see from this plot is that inference is really just a subset of training. So this table just illustrates what some of these key differences are. So let me actually just bring up the whole table. So as we mentioned, the compute phase point of view, there are 3 compute phases for training. There's only 1 for inference. The batch size is the data that we started with, which is usually very large for a training set, could be large or small for an inference example. The memory footprint, though, for training tends to be very large. And this is because we have the weights. We also have activations, which have to remain around as we as we pass through. And when we do the back propagation step that you saw before, we have to retain a lot of the results that we generated during the forward propagation step. So that really increases the memory requirements. From a system point of view, training usually happens in a distributed system with a number of different accelerators or GPUs. Inference, this is an older table, is usually a single device affair. But as you were seeing, these model sizes are becoming so large that we're now beginning to think of inference in terms of multiple devices as well. And the key thing for training is really throughput. Whereas for inference, there are many cases where we really care about latency, because obviously we want to be able to tell whether there's a pedestrian in front of us really fast. So some of the compute requirements, these are some of the various networks. And there's really a need to accelerate diverse networks using training for both training and inference. But despite the differences in these networks, there's relatively a small set of building block operations that are used by all networks. And deep learning algorithms are particularly suited for hardware acceleration. This was a study that was done a few years ago, and it basically found that 70% of the operations are either matrix multiplications or what are known as convolutions. So there's a lot of commonality here and a lot of opportunity to accelerate using specialized accelerators. So this is an example of some of the things that are done to accelerate AI workloads. One thing is the use of a data flow architecture. So because the matrix operations are so dominant and the convolutional operations are so dominant, these can be set up using a data flow architecture, which really just passes the right arguments over to each adjacent processing element and in a very efficient way. So GPUs are very good at doing this. So are these kinds of specialized architectures. An example is shown here. And the other thing that can be leveraged here is that the networks are really predictable. So we know exactly what data structures need to be brought in at what time. So it's a little bit different from a cache where you're trying to guess what data should you keep in your cache. Here you can put scratch pads, and if you use your compiler correctly, you can actually just predict what data structure I need to bring in. So for example, if I'm sitting on layer N in the network that you saw before, I'm going to kind of know that the next thing I need to do is bring in layer N plus 1. So by doing this, we can really wisely use scratch pad memories that are close to the chip and therefore reduce the time and energy required to bring the structures that we need to the processing elements. The other big feature in a lot of these accelerators is reduced precision. And this started a few years ago, you can see around 2015, with the recognition that AI workloads simply don't need the precision that many of the other high performance computing workloads did. And this is kind of akin to our brain, where we don't really have to calculate to a large degree of precision to figure out whether something is a cat or a dog. Our brains are able to do that with a lot lower level of precision. And this is actually seen very commonly in AI workloads as well. So you can see the progression here where training was being done. That's the top line, with 16 bits and inference at 8 bits. Then we went to training at 8, inference at 4. And today we have demonstrated training with 4 bits and inference with 2 bits. Now, what you might see sometimes is that when you do this, you get a loss of accuracy. But these results that you see here have no real loss of accuracy. So it's really just nothing but a pure gain situation to go to lower precision and preserve accuracy at the same time, leveraging the quadratic gains in energy and area. So you can make things smaller and you consume less power as well. So what do we have in terms of memory requirements? So far, we've talked about the compute requirements. And the real key here is that first sentence, which is that memory bandwidth has to increase in proportion to compute gains. So if we can just make the compute faster, we're not going to win, because we aren't able to feed those compute units or the processing elements with data. So they're just going to sit idle, and we don't get an overall system benefit. So the system can otherwise, if you don't really do this, the system just becomes imbalanced, and that leads to low utilization. So one way around this is with the on-chip scratch pads that we saw before, and that's a great opportunity for heterogeneous integration, and I'll talk a little bit more about that later. The other key point is on the capacity, which is processors need fast access to these large models, and we saw how the model sizes are just increasing very, very rapidly, and that means that can introduce a lot of delay and energy consumption in just bringing in those weight parameters from an off-chip memory, or even worse, from storage. So from a training point of view, as we said, you have a lot of data structures, and these need to be kept close to the processors. And the key here really is the throughput. For inference, there are fewer data structures. The on-chip model storage becomes very beneficial because you're really focusing on latency. And as we said, for real-time applications, latency can be very critically important. So let me talk a little bit about the bandwidth. And for this, we did some simulations using a multi-chip network of AI accelerators, in this case, running a network called ResNet 50. So each of these chips that you see in a gray box has several of the AI cores from this paper that you see cited here from IBM. And what we did was a little study that you see on the right. So it's as if we could, maybe if we had a genie who granted us one wish, and we said, the genie said, well, I'll either allow you to double your compute or double your bandwidth. Which one would you choose? So we did a little study, and we found that given our current architecture, if we just doubled the compute only, that's the blue curve, our overall system performance would quickly saturate because we're not able to feed data to that increased compute fast enough. On the other hand, if we just increase the bandwidth, we get a little bit better gain. That's the red curve that you see here. But the best gain was when we really do these two things in tandem and create a balanced system. That's the green curve, and that's where we achieve the maximum system benefit. So from a capacity point of view, larger models just need more capacity. And this shows a progression of these models from left to right, showing how much larger their footprint in the memory is. That doesn't include actually just the weight parameters, which are the dark blue, but it also includes other things such as optimizers and feature maps. And you can see that that footprint just gets larger and larger. And correspondingly, the GPUs have responded by having higher capacities. That's the dashed line. But both of these things are just increasing at a very rapid rate. So lastly on this topic, I'd like to talk a little bit about connectivity. So this chart was made really focused on training. Because training is such a compute-intensive job, it can be parallelized amongst many chips or workers. One example is shown here. This uses an algorithm known as data parallelism. So in data parallelism, what you do is you make multiple copies of the model, and then you just feed a certain portion of the data to each worker in the system. And then each worker is able to process that set of data. But what happens is for each worker, you'll get a different change in the weights because each worker operated on a different set of the data. So then they all have to come to an agreement about what is the right weight change. So they exchange amongst each other. And that communication cost can actually be very, very appreciable in one of these systems. So getting high connectivity amongst these chips is really critical. And if you don't really properly account for it, that cannot dominate your training time. Now, again, this chart was really made when we were talking about training as being the workload that requires a lot of workers. But as you were seeing earlier, these model sizes are becoming so large that they are surpassing the memory capacity of a single accelerator or a single GPU. So even inference is now moving towards having multiple workers. And there, the partitioning problem of how do you partition a particular workload is also becoming an active area of study. So again, I won't go into that, but I'd like to kind of point out that it's not just for training anymore, that we're really talking about these distributed systems. So this is a very nice chart that shows how the hardware capacity, the flops, the compute throughput has scaled along with the DRAM bandwidth and the interconnect bandwidth. And what you see pretty clearly from this is compute has continued to go up. That's the gray curve up at the top. But DRAM bandwidth and interconnect bandwidth have really not scaled in the same way. And what this has led to is a performance bottleneck from the accelerators to the memories, making sure that enough data is able to get to the accelerators, and between accelerators for the connectivity that we just talked about, accelerator to accelerator. And if there's a mismatch between the compute and the bandwidth gains, then you get low overall system utilization. So I don't want to spend too much time on this chart. I think most people will recognize that scaling is really stalled at this point. And you see that in the left chart, single thread performance has really saturated. Power has imposed a severe limit. And typically now the way around this to circumvent this is by parallelism, a throughput-centric model in which you have a lot of cores. And those cores are able to operate in parallel. So density gains are really critical. Fortunately, density has not really stopped scaling. So density scaling continues, but the net single thread performance is really saturated. But if we want to continue to make progress with these ever larger AI models and their demands, we really have to find a new paradigm. So to quickly summarize, what would we like to get out of HI to accelerate AI? From a compute point of view, we need a lot of dense compute with optimized architectures for AI. From a memory point of view, we have to look at both the capacity for larger models as well as the high bandwidth to match the gains in the compute throughput. And from a connectivity point of view, what we need are energy efficient interfaces for high bandwidth connectivity between these various compute elements. So advanced packaging and heterogeneous integration are really critical to address these bottlenecks and improve the overall system performance. So now let me switch gears a little bit and talk about heterogeneous integration. A little bit of the motivation, which I probably don't need to do much of for this audience. What is there out there today, and then where are we going? So from packaging to heterogeneous integration. So here are two paradigms. For a long time, we tried to get everything on the same chip, and that was called a system on a chip. And we'd integrate various components monolithically onto a system on a chip. Another way is to put everything on a package, system on a package, integrate components as separate chips on a single module or package. So what is heterogeneous integration doing beyond that, and how is it distinguished from just packaging? With heterogeneous integration, the goal is to integrate separately manufactured components, which I'm now going to call chiplets, using advanced packaging techniques with high density interconnects to achieve enhanced functionality and improved operating characteristics. So you see this in the cartoon on the bottom right. This might even be a first level package which gets placed on a next level package, and this first level package has much higher density interconnects. It could be a silicon interposer, for example, or a number of other packaging platforms. And the goal here is to really get high density interconnects between these various chiplets. And that may take the form of going horizontally, or it may also take the form of 3D, where we are stacking chiplets one on top of the other to really get to higher bandwidths and lower energies. So why is this really a golden opportunity for HI? First off, node optimization. It's getting very, very expensive. The number of players and the number of foundries that are able to produce very leading edge nodes is really diminishing, and the costs are going up, particularly with EUV. So it really is desirable if we could break up a really big chip into several smaller pieces and only scale the parts of that chip that will benefit from the advanced scaling. So this was exactly the trick that was played, for example, by AMD on their EPIC. You see the big 14 nanometer IO chip or chiplet, however you want to call it, in the center, and then the 7 nanometer CPU smaller chips off on the side. So those will benefit from the scaling. The IO not so much. So it's okay if you leave that behind in 14 nanometers and do the advanced scaling only on the processor parts. Intel has done something also there with Ponte Vecchio. You can see the 40 plus chiplets that are assembled on this package. So again, these are all from different sources, different nodes, different functionalities, and they can be placed on a package to get a very high silicon density in a certain area, much higher than you would achieve if you had to do this monolithically and package every big chip separate. Another big advantage is in the die disaggregation. The cost, these smaller dies have much higher yield. So there isn't that benefit, but just to be careful, there's no such thing as a free lunch. You now have to add interfaces, so that does add to the cost. But the net, there is still generally speaking, a net win when you do this. The other big advantage is modularity. You can flexibly compose optimally sized system for the application. For example, on the left top in this AMD EPIC, you could omit some of the CPU chips and create a smaller chip because you've now got smaller building blocks to use. There's some more examples on the bottom. I'd like to point out particularly the one on the bottom right. That's where NVIDIA took one of its GPUs and essentially cut it up into 36 little pieces or chiplets and assembled them on a package. And they were able to show that they can achieve equivalent performance with this as they could with the original larger monolithic chip. So heterogeneous integration is being leveraged very frequently in AI today. Examples of this include the NVIDIA GPUs, the Ampere shown on the left, with 6 HBMs on a large silicon interposer. On the upper right, an AMD GPU here, you can see a blow up of the high bandwidth memory with 3D stacking of the memory on the right-hand side. Again, on a silicon interposer for high bandwidth connectivity. But there's still many ways that we can continue for future research. One is in lower cost, higher scalability, higher bandwidth and capacity, lower power, and more compact form factors. Also would be an area for future research. So let me now turn to where do we see heterogeneous integration moving. So this is a taxonomy of some of the HI approaches. On the left, you see the interposer approach, which could be either silicon or with thin films, an organic type of approach. The silicon one is pretty well established, the silicon interposers that we saw on the last chart. Organic ones are still emerging. Another approach is with redistribution wiring. Silicon bridges are one example of this, and wafer level fan out is another example that's been so far confined more to the mobile space, but shows a lot of potential as we try to move that towards higher end applications. And then way to the right of this in green, you see 3D integration. And that's really where we see a lot of the future and the potential. The reason this is often a different color is that it is fundamentally different in some sense because it does require a change at the die level, whereas the other two, really you could do them in a format or in a platform where you preserve the dies and then you use these various platforms for joining and assembling. But on the right, you have to plan ahead and put those TSVs in and really make that design. Now, why is this really interesting? Let me backtrack just slightly, talk about the 2D or the 2.5D silicon interposer case, which is very established at this point, but has the disadvantages of being high cost and also being of limited scalability. So there's a large effort right now to find alternatives to silicon interposers. These include bridges, wafer level fan out, and high density organic substrates. But what I really want to spend a little bit more time on is 3D and why it really holds some promise for AI. One reason is the high bandwidths. Now, off-chip memory bandwidth is really limited by the packaging features. So the memory bandwidth has to keep increasing in proportion to those gains in compute. Otherwise, you won't really see an overall system benefit. And if you try to access things off-chip, that's actually energetically a very expensive operation. And there's a table on the bottom right, which just compares the cost of a 32-bit add to a 32-bit on-chip SRAM cache access or a 32-bit off-chip DRAM access. And you can see that those are vastly more energetically costly than even doing some simple floating point operation on the chip. So there's a huge incentive to just bring the data closer to where the processing actually happens. Thirdly, capacity. So 3D stacked memory is just like getting more memory on chip. And we saw earlier when we talked about the architectures, why this is so beneficial, to be able to access weights or store activations on chip and not have to go off chip to get that same data. So this is particularly useful for large models. And then the fourth one is really kind of a little bit aesthetic, but it also has to do with cost, which is the form factor. It's just better if we can keep everything confined to smaller spaces, even if that means that we have to go vertical rather than going to larger body sizes and larger packages and putting a lot of packages of memory down for an accelerator. So some of these benefits are shown in the plots on the upper right and then summarized in the table on the lower left. From a bandwidth perspective, we can go from hundreds of gigabytes per second with these 2.xd types of solutions to terabytes per second with the 3D. You can see how this scales with the plot on the upper right. I think one of the most exciting developments right now is really in the area of hybrid bonding, which is getting to sub 10 micron types of pitches, and that tremendously increases the bandwidth potential. The other big benefit is really in the energy per bit. So where you have to drive it across in 2D, which means also that you have to not only have a longer distance and higher parasitics, but also account for more ESD protection. That just leads to higher values of the energy per bit. If we can do things compactly in 3D, distances are a lot shorter, processes can be controlled, ESD requirements aren't as strong, and the energy per bit can drop very significantly. And when you're dealing with a lot of data, that's just more power that can be devoted to the compute instead of being burned away in trying to retrieve the data. So where are we with 3D? The current state is 3D has been long in production for low power applications where we're stacking, say, memory. But the desired place to go is really being now able to combine logic and memory, or creating some kind of memory and accelerator stack. So one promising development in this direction was the AMD Ryzen announcement. There they do have a processor on the bottom, and then on the top they're stacking 3D SRAM on top of on a CPU. So mixing memory with logic. So one thing that always has to be kept in mind with 3D is that the thermal requirements are very stringent. This has been a constant kind of bug when we talk about 3D. So cooling and power delivery are both major challenges. This does affect sometimes the question of, do we put the more power hungry component on the top, in which case you've got to feed it through the bottom, or do we put but the cooling is a little bit easier, or do we do the opposite, put the power hungry component on the bottom so it's easy to supply. But then if it's the hotter component, all of that heat has to be escaped up through the top, and that can lead to some significant thermal challenges. There are certainly some good directions in this area. One of them is in dual side cooling, so you can cool both the top and the bottom. The other is might be in embedded two-phase dielectric chip cooling, where you force the cooling fluid in between the components in microchannels. So let me just take a little bit of a turn here to talk about IBM's work in this area through the chiplet research ecosystem, which stretches across many of our research sites as well as IBM systems. We've grown into a collaborative ecosystem with more than 10 partners from across the supply chain, including everything from equipment to materials to EDA, research and manufacturing. This is in the AI Hardware Center. You can take a look online, which is centered at the Albany research site, not too far from here. And these are some of the particular thrust areas for us in heterogeneous integration. On the left, you can see a high density interconnect laminate, which enables access to tight pitch die interconnects at lower cost than a silicon interposer. In the middle, you see work on silicon bridges. And then on the right is the 3D integration that we were just talking about, which gives the highest interconnect density and most scalable solution, and is particularly interesting for stacking combinations of accelerators and memories. Now, if you look at the timeline for these, there's kind of an increasing level of complexity and time to market as you go from left to right. So now that we've talked about both the AI aspect and the HI aspect, let me tie these together with a path forward. So we really have gone from packaging, plain old packaging, to heterogeneous computing. So if you look at the left of this up to 2015, it really was siloed in terms of the applications, depending on whether we were talking about mobile or whether we were talking about GPUs or CPUs. And pretty much we were talking still about packaging together very similar kinds of components. From 2015 to 2021, there's increasing heterogeneity. And then from 2021 right now to, for the next 5 years or so, we're really in a regime where that siloing has really grayed out. And solutions that were thought of for one of these particular spaces is really being looked at for other spaces. I mean, for a good example is wafer level fan out, which has been more of a, for mobile applications, and is really now also being thought of possibly for high performance applications. But all of this is leading to an era of true heterogeneous compute, where we can have really a fabric on which we could put dilets or chiplets and create very heterogeneous domain-specific architectures using these kinds of building blocks. And an example is at the bottom right, an HI-based accelerator package. But in order to really facilitate this, it's first important to recognize that these different use cases have very different requirements, yet we still want to build them from similar kinds of blocks. So, IoTs and sensors and mobile applications might require only small core counts and have, lower power requirements, whereas automotive will be a little bit higher, and a data center application has a higher power envelope and requires a lot more compute power, tends to hundreds of cores. So even though these are different, it really still would help to have a set of building blocks from which we could compose into these various spaces. And chiplets really offer that composability and scalability solution for a wide variety of use cases. So what's really key towards this vision of heterogeneous compute? So one thing that's really talked about a lot and that we are great supporters of is an open chiplet ecosystem. So right now, chiplets are being used. You saw examples from AMD and from Intel. The problem is that they're typically from single or limited sourcing. They don't really talk to each other, and they have proprietary interfaces that are really specific to that source. You can't mix and match them. Now think about a future where you could mix and match. Just like when you buy a car, you're not confined to one tire manufacturer if you get a flat tire. You have your choice of, there's a standard, and they will all fit on your car. If we could do that with IP in a chiplet format, we could really mix and match a lot of different components and create very heterogeneous architectures. So the vision here is for a chiplet supermarket with a large catalog of soft IP, hard IP, and full chiplets from many vendors that could actually talk to each other. And this would greatly lower the barrier to innovation by leveraging smaller, low-cost dies and IP reuse. And since we're here in a university setting, I think this is even a bigger benefit for universities, because this means that it will really lower the barrier towards producing a full system. You don't actually have to tape out a big SoC to get results. You can leverage reuse from other IP that might be available in this ecosystem and create your own special part that just talks to these. You don't have to create a high-speed SerDes interface, for example, to realize the functionality of a chip. So why is, this is such a great idea, why has this not really happened yet? Well, right now there's no universally accepted die-to-die open standard. That's one problem. There's a lot of effort in this area. And then there's a chicken and egg problem in really creating this chiplet library, in the sense that it does require a lot of initial investment, and kind of nobody's yet really stepped up to do this, to be first, kind of. So once there's momentum, we think that this can really take off and literally change the paradigm for heterogeneous integration. So where does that leave us? This is just a kind of some closing thoughts. Heterogeneous integration can enable heterogeneous computing with these diverse chiplet building blocks. What's desired is high compute density, tiling of multi-core chiplets, the ability to put in specialized components, which could include 3D or other specialized accelerators, high bandwidth and low power interfaces, which connect all of these. And also you can see in this picture some memory. What do we want in terms of these interfaces? High bandwidth, energy efficiency, area efficiency, so they don't take up too much overhead room on the chips or chiplets themselves, and standards which would allow connectivity between chiplets of different sources. Now, I haven't talked about a lot of the other issues as well, but you can also think that this really does open up research avenues and things like security, where you're now multi-sourcing chiplets to combine them together, and a lot of other different test is another big area. So there are potentially many different areas which could be researched around this type of a chiplet ecosystem. The heterogeneous integration technologies would play a central role in this, and you could see a roadmap where architectures are developed using some current technology, and then as packaging technology improves, bandwidths can go up because feature sizes get smaller, and those could be really leveraged in this type of a chiplet architecture. With that, I think that's my last slide. I will close and open it up for any questions. Thank you. Mhm. So if I somehow omitted that application, I apologize, but I didn't intend to. And in fact, I think that's a very interesting and exciting application. And just to be very clear about it, you know, to exemplify it, if a medical company had a processor or something, or you know, that took medical data, the beauty of chiplets is you could combine that with a small AI chiplet that somebody else made. They don't have to develop themselves. And as long as these two chiplets could communicate, and there is a reasonably costed packaging platform to combine them, you know, I think the opportunity there is very large. Yeah, that's the big point. You don't have to do everything yourself anymore. Sure.
Thank you, Arvind. Now we are ready for our next talk by James Sexton on future computing challenges and opportunities. Dr. Sexton is an IBM fellow working on future systems architecture at IBM T.J. Watson Research Center in New York, and Dr. Sexton received his PhD in theoretical physics from Columbia University. His areas of interest is in high-performance computing, computational science, applied mathematics, and analytics. Prior to joining IBM, Dr. Sexton held appointments as a lecturer, then professor at Trinity College Dublin, and as postdoctoral fellow at IBM T.J. Watson Research Center. At the Institute for Advanced Study at Princeton and at Fermi National Accelerator Lab. Thank you, Dr. Sexton, for being here.
So thank you very much. I'm going to follow on some of the comments that Arvind, some of the material that Arvind has presented here. I think Arvind covered very well what's happening inside a chip and inside a module. I wanted to come down from a very high level and show you what's happening in at least one area of future computing. I'm not going to be talking about I would call it edge computing, the small chips that live in sensors, the small chips that live in devices. I'm really talking about large-scale compute and where that's going and some of the challenges that it's bringing into play. So one of the things that is very obvious to those of us who've worked in computing for a very, very long time is that what we're looking at today in terms of large-scale computing is fundamentally different than anything we've seen in the past. I mean, we have this emergence of one of the big things that's happening is data. We're getting data at unprecedented scales, unprecedented reliability, and we're getting tools that allow you to look at that data and understand features in the data, apply AI to that data. And so data is a driver, then AI is coming in as a technology that really is a whole new capability that we've never had before. I mean, the last big breakthrough in using computing to understand systems was probably in the 30s and 40s of the last century, when we learned how to do modeling and simulation. It was basically developing understanding of partial differential equations. That was kind of the breakthrough that allowed an enormous amount of compute to happen over the last century. We're now in a whole new phase. And that whole new phase, that AI is one piece of the puzzle. The second piece of the puzzle is that data is everywhere. It's not in a data center anymore. It's scattered everywhere. So when you build computers, you have to plan that you can actually touch and find and use that data where it is. You might say, well, move it all to the data center. Forget it. There's too much data out there. So you have to be able to build systems and connect where the data is. Using AI, using quantum, and some of the new techniques impose new architecture requirements on us. So we have to rethink the way. Von Neumann was a great architecture for doing partial differential equations. It's not obvious it's the right architecture anymore for what's coming. And then finally, and this is where Arvind spent a lot of time talking, everything depends on being able to build really effective microelectronics to support what we're trying to do here. So as an example of kind of the way a large-scale systems person thinks about computing, it starts at the top. We have many, many different things we want to do with data. We want to do processing or traditional processing, but we also want to do modeling and simulation. We also want to do learning on the data, inferencing on the data. And these are just sort of, you could draw 100 boxes on this top here. I wanted to give you a feel. There are many different things that are happening that you want to do. And one of the challenges that's arising is you don't necessarily want to just pick one and focus on that. You want to do them all at the same time. You want to learn on data as you're actually analyzing it. Examples might be financial institutions that are watching what's going on in the markets. Well, they're doing some market analysis, but they also want to check that nobody is doing bad things. There's no bad actors in there. So you're doing a lot of modeling and inferencing of what's happening in the data flows to look for things. On top of that, we're finding that you don't do everything in one place anymore. You're really taking advantage of this, what we call hybrid cloud techniques, where sometimes a piece of your workflow is sitting in a data center in New York, another piece might be sitting in a data center in San Francisco, and yet the two have to work together and connect together. So I have a problem in how I put all that together. And then at the bottom, I have to figure out where I'm actually going to run each given piece of data. And more often than not, the decision is made by where the data is rather than by where the compute is. Where in the past, we've always brought the data to compute. That's not a direction. We're seeing now a realization in future computing of a very, very old paradigm that you're all very familiar with. This is this paradigm of the scientific method, which is really a paradigm that says you have a problem, you study the problem, you hypothesize about how the systems underlying the problem might behave, you test those hypotheses, assess. So you have this big complex loop that applies in research. We're very familiar with it in research, but it applies also in enterprise. I mean, when you're making decisions, if you're an oil and gas company, you're making decisions about where you're going to drill or how you're going to build renewables, it's the same process. If you're a government and you're making decisions about how we're going to manage climate change, it's the same kind of thing. We have enough data out there now that we can actually plan to execute a full loop of this kind of process to give us much better results than we've had in the past. It's all enabled by compute. Here's one particular example of what we've been doing inside IBM Research is looking at the study of photoelectric materials. We've been using computing, different types of computing. We're using, on the lower left, something we call deep search, which is we're trying to study and develop new photoelectric materials. So we begin by ingesting a whole corpus of knowledge. Every paper that was written on a given area, we ingest and build a knowledge base from. That's a starting point. So now you have a very, very broad knowledge base to work on. You can use modeling and simulation to study and fill in gaps. You can use AI techniques to hypothesize about new possible materials. And you can even go, and then we have now managed to build robot labs to do the synthesis of those materials robotically without any, you just apply. So we have a loop that can run very, very quickly. And last year on this loop, we were able to generate 2 candidates in less than 6-month period for new types of materials that are now undergoing follow-on testing. But this type of behavior and capability is something that's going to be coming across every domain, enterprise, government, and research. And it requires incredible amounts of computing. And therein lies a problem, a really big problem, which is the power that our computing in the world is using today is starting to swamp everything else. So we have a huge amount of power feeding into data centers. And we have a projection on the next page that says within a few years, 10% of the total power in the world will go to feeding and powering computers. It's not sustainable. We have the example on the AI side, very, very, very real opportunity there, but it's a huge power-hungry beast to actually keep fed. And then, and we're not getting real help on the silicon side. I mean, the tradition had been that you could, every year you get more performance simply by using Dennard scaling. We're not getting that anymore. So we need different techniques. The methodology, the possibility. So here's the measurement. Increase per year in energy consumption for data centers. And by 2030, the current estimate says 10% of the total power we generate in the world will go into data centers. That's not sustainable. And yet, the opportunity to solve really hard problems is sitting there with all of this compute power. This chart, and Arvind touched on it in his talk as well, you continue to see a growth, an improvement in technology, silicon technology. We're continuing to be able to increase density. But for me as a systems architect, we're able to improve performance per chip, but we're doing so by adding more and more compute units on the chip. So I'm getting more performance in a chip, but now I have to get more stuff into the chip to see things. And Arvind was talking about 3D packaging, memory packaging. These are examples of some of the problems we have to deal with. The power isn't really changing. Power per chip is staying pretty much flat. The cost per transistor is going up, which is an interesting observation. Even though you're getting more on the chips are getting more expensive to build. It's more expensive technology. It's extreme UV. It's much more complex packaging. And so we're sort of stuck in a catch-22. We have incredible capability coming, but we don't know how to manage the power requirements and deliver the systems requirements. The consequence Arvind talked about is heterogeneity. Arvind talked about heterogeneity inside the chip, but it's everywhere in the system. It's inside the module. It's inside a physical node. We're not seeing the way we traditionally build computer nodes, a board with a CPU and memory on it. Well, we're seeing more and more heterogeneity there. And then we're seeing heterogeneity in the data center. You're having different types of compute in the data center, but across data centers as well. So a person using large-scale compute is no longer running on one computer of one type. They're running on multiple types of computing elements scattered across multiple geographic locations. And so we see many, many players here. The picture here shows some of IBM's approaches. I mean, the AI devices, the quantum devices. One of the things we're working on my side is, can I build a fabric? Arvind talked about a fabric inside the module to connect chiplets. Can I build a fabric between modules to easily connect different types of compute? And CXL is emerging as a very, very interesting candidate in that space. Within the data center, we see this kind of composability now also coming. This is some data from IDC, this idea of composable disaggregated infrastructure. So can I build, the way I think about it, I can build a module which is my CPU, and Arvind talked about putting memory on the CPU or putting memory on my accelerator or putting memory on a special device. When I have that kind of building block, it's a standalone building block. It can boot itself. It can launch its own OS management system. So now can I take those building blocks? I no longer have to build node boards. I can take those building blocks and just plug them in as pluggable units on a composable fabric. This is a direction that we see coming. And the reason I'm bringing it up, of course, is how we build these fabrics, how we do optics to support this kind of interconnect are very, very important opportunities for the space you guys are working in. And so, but composable It's built out of two kinds of core elements that are coming. So your compute, your memory, your network, your storage, they're disaggregated. They're not assembled on a single node the way we've traditionally imagined, but they're assembled in blocks connected on an optics and an electrical fabric. And then you build a very complex software capability to put all of this together and manage it for you on demand. It's from a market perspective, it's considered to be an evolution of what's called integrated and hyper-converged infrastructure, but very much it's something that's coming. And IDC has an interesting comment. Not only are you changing the way you build silicon and chips and chiplets, but we're going to be changing the way we build large-scale computers as we go forward too. And so in our instance, the other piece of the puzzle that's really changing the way people think about computing is this idea of hybrid cloud, where cloud has been around for a while, but if you're not watching carefully, it's gone through a number of phases. We're in a phase now where cloud is now disaggregated and decentralized. No enterprise commits all of their business to one cloud provider in one data center. Every serious enterprise commits business across multiple cloud providers, multiple data centers for security and flexibility and safety. And so another piece of the puzzle that's coming is from a very high level. As we think about building systems, we need to think about how those systems can be secured, how you as a user or an enterprise as a user can secure your data no matter where it is. And that imposes constraints on the hardware suppliers, the builders of the silicon, because security now becomes really critical. Things like we're very open to the idea of memory and bits in that memory. Well, encryption of that data in that memory now becomes a very important piece of the puzzle going forward. It's going to be hard to survive if you cannot provide encryption everywhere. And so that's in your memory, on your interfaces, on your networking, in your CPUs. Because otherwise people are not going to be able to use this technology. The ones that can use this technology are the ones that are going to advance. So an opportunity is, as you're thinking about how silicon is evolving, how do we change the paradigm so it's not raw bits and bytes that are there open, that they're secured in some way. The thing that comes after you've done all of this is now think about an end user, a client, an oil and gas company, a government agency that wants to establish a model of, or wants to build an application that actually studies a really complex problem. They will have many, many different applications. And on the left-hand side at the top, they will have catalogs of applications you want to run. So some of them will be data analysis, some of them will be modeling, some of them will be AI. They will have data that they want to run on. So they will have complex catalogs of data. And a lot of the data we have today comes with compliance and geographical restrictions. Many enterprises, many countries now no longer allow their country's data outside their geography. And so if you want to work on let's say, an oil company working on seismic data that they've collected in Mexico, they have to do the processing in Mexico. And so there's these geographical problems you have to worry about as well. And then you have an incredibly complex and rich set of resources on which you can compute. I mean, you have multiple cloud locations you can run on, multiple compute types, multiple memory types. We are envisaging that one of the uses of AI going forward is to help the end user select and optimize the right mix of resources. And this picture is just on the left-hand side, I have sets of building blocks. On the right-hand side, I have a user who wants to run a set of workflows. I have to build a complex AI-based engine in the middle. put them all together and make it run efficiently. And not only do I do that just to make the applications work well, but to manage my power. You can make significant power savings if you do this right as part of this AI. You can allocate your work you can run it at nighttime, for example, where energy costs. You can do lots of clever things. So the decision on when you run a piece of work, where you run it, how you run it, what hardware you run it on, is not just about the work, it's also about the power you're using, it's also about the availability of resources, et cetera. It's going to become a very, very challenging problem. We do see this emergence of, in fact, as a stage along the way, multiple types of computers, of clusters of computing. I mean, we have our traditional general purpose computing that we're all very familiar with. We're going to see more and more specialist computing also showing up as part of the mix. And so the user will have to figure out how to deploy and optimize. So AI type computers, modeling and simulation type computers, quantum computers. And one of the very interesting developments over the last few years is the emergence of a whole software stack that allows you to run usefully in this kind of ecosystem. And that software stack is based on Kubernetes. IBM's OpenShift is an enterprise version of Kubernetes. It allows you to provision on-demand resources across geographies, across hybrid cloud. Is a key piece of our ability to move forward. So how do I go forward? Well, in terms of computing, the phases we're seeing is taking advantage of what we have today. Then how do I make accelerators more efficient? I mean, one of the problems you have with accelerators is they're really great when you're running exactly the right thing on them. When you're not running the right thing on them, they're just sitting there generating and burning power and not being very useful. We did an analysis on one of our supercomputers a few years ago that said, had a lot of GPUs in it, but when you actually looked and asked when was that GPUs doing useful work, it was less than 10% of the total time. Even though the computer was fully occupied, at less than 10% of the time was the GPU actually doing work. That's not, when I'm looking at a power budget that says 10% of the total power in the world is going to be in data centers in 10 years' time, that's not acceptable. We have to find better ways. And so in terms of electronics and microelectronics, how do I build hardware that's on off really easily, that I can turn on and off, that I can enable, connect, dynamically configure, reconnect, redynamically configure, and in very, very short time scales, because otherwise I'm not going to be able to afford the power that I'm going to. And then as we move forward even further, you're talking about new types of computational models and underlying microelectronics to support them. So quantum is an example, non-analog maybe, non-von Neumann technologies. And so let me finish and say the challenges and the opportunities we can see. Power requirements are dominating our thinking as we think about very large computers. The emergence of special hardware is critical, but today it's not very well used. So I need techniques and methods and connection capabilities and fabrics that allow me to use that special purpose hardware exactly when I need it, but not have it sitting there burning power when it's not needed. So that means how I connect things together, optical interfaces to connect things together efficiently become really, really critical. Power management techniques where I can turn things on and off, etc. I need new packaging methods, new memory technologies, new fabric technologies, because I have to be incredibly efficient with the transistors that I lay down. I can't have wasted transistors anymore. They're going up in price, so I have to continue to be very efficient and do that. Obviously, new computing models. Obviously, no single supplier can put all this together. So that means you have to have standards. You have to agree standards in the module, between modules, as you build computers, so different players can build different pieces and they all come together and work together. So, and on the right-hand side, I talk about we're expecting increasing heterogeneity, increasing complexity, increasing need and opportunity for composability at all levels in the system, inside the module, inside a single system, and between systems. And then not only are we using AI for the applications, but we're expecting to have to use AI to actually manage and deploy workloads on these systems as well. So let me stop there and say thank you for your time today.
Questions? Thank you, Jim. It was exciting as well as scary to know about the new materials that could be created by AI. You know, don't have to go to Mars or other planet and dress up as avatars to to find new materials or unobtainiums looks like. Okay, as I say that, let's go in seamlessly into the next talk by Dr. Hemanth Jagannathan on Foresights on CMOS technology scaling to 2 nanometers and beyond. So a short introduction for Dr. Jagannathan. Dr. Jagannathan is a hardware technologist and principal research staff member at IBM, where he conducts research on advanced semiconductor hardware technology. Dr. Jagannathan has driven many key technical advancements for several generations of semiconductor technologies, ranging from planar, FinFET to stacked nanosheet and beyond nanosheet device architectures. He is the executive director for SUNY IBM Artificial Intelligence Collaborative Research Alliance, where he oversees joint AI research ranging from hardware algorithms to software and applications. Dr. Jagannathan is a recipient of multiple IBM Outstanding Technical Achievement Awards and Research Division Awards for his technical accomplishments. He's a senior member at IEEE and member at large in electronics and photonics divisions of Electrochemical Society. He has published over 90 papers and is an IBM master inventor holding over 200 US patents. He received his PhD in electrical engineering from Stanford. Welcome, Dr. Jagannathan.
Thank you, Satya. I have the pleasure of being the talk before a 30-minute break, and I think I'm over. So I can sum up my talk in a few sentences that the future is bright. We have a lot to look out for, but you just met me, so why do you trust me, right? So let me maybe take you through the journey as quickly as I can and kind of explain at least my view of what we expect to see in the future. And the beauty about my talk is that I'm predicting things in the future, but I will show things in the past because it is based off of what we have done so far. You know, the future is always something which cannot be predicted 100%, but it's still quite bright. So with regards to this audience here, I don't really need to spend too much time on this chart. You know, computing is everywhere. We are always craving for faster computing, and as a result also need to be energy efficient. So we, in the semiconductor technology business, we live and die by certain principles. The power performance area cost paradigm is one such principle. We obviously need to make sure that the power of the chips which we build are manageable. We are always trying to reduce the power consumption. We also try to improve the energy efficiency from generation to generation, knowing that we are trying to cram in more transistors. When you look at the area, part of Moore's law is really to scale the size of transistors and also reduce the size. Once you reduce unit size, accommodate and cram in more transistors. And that's been done successfully over the years. And we are standing here enjoying the fruits of those many decades of labor. Performance is very important. We want to buy the newest gadgets, but we want to also have it faster, you know, seamless experiences from various applications. Jim had mentioned about optimizations done in the systems level, but even from consumer electronics, there's lots of you know, real world examples where you really crave performance. And at the end of the day, is the cost. When it hits the bottom dollar, you want to make sure that this is something which is affordable. So you want to have reduced cost, or at least nowadays at parity cost as you get higher performance and higher capacities and higher storage and all that good stuff. So in order to understand the PPAC, when you look at the roadmap of pushing the scaling of transistors, you see that conventional scaling, as we know it, really ended in the mid 2000s, around 2005. A lot of this scaling happened with physics, electrostatics, and all the node names started evaporating around that time frame. And device architectures, innovations, material breakthroughs are really the key reasons for why we have seen onward progress from 2005 onwards. So the end of Dennard's scaling law doesn't mean the end of Moore's law or end of scaling. At least my opinion is that scaling will end once human ingenuity ends. And you can see here that we have done quite well over the years, and there is still a lot of steam at the end of the tunnel. So when you look at CMOS technology advancements, this is a picture. I didn't go down to the micron regimes, but I started at like hundreds of nanometers, all the way down to where we are at around 7 nanometers. We see that there's been a lot of transition from the DNA of the chip. So in this case, we are focusing on the transistor. And you see that we were primarily dominated by planar transistors in the early 2000s. And we migrated over to FinFETs around the 22 nanometer node. And what you see here is that it is this technology advancement and process innovation which really kept the sustaining engine for the semiconductor technology industry. We are now at the precipice where we are seeing this FinFET technology losing steam. There are some fundamental technology challenges. And it is also widely known that there are multiple innovations which have now been adopted, like gate all-around technology, such as stacked nanosheets, which are being adopted by many of the major foundry players in the world. So the net message here is that you can see that every node has changed dramatically. It's even though there was a planar, these 4 nodes are all planar, each node had brought in new elements like stress technologies, high-k metal gate, going to thin substrates, moving from thin substrates to FinFETs, to really tall FinFETs, and now gate all around. So we have never stayed still in any node. And that takes a lot of ingenuity, engineering to get the final chip level, system level performance, which we all crave. So if we now look at, step back and understand why is this now becoming so difficult, and why can't I say this will go on for hundreds of years? I would, but then you'd have to buy me a drink and really make me lose my mind. Right now, I can see that this can go on for a couple of decades. And that's the reason is because scaling is extremely challenging. We have taken it for granted for many, many years, but the scaling is really tied by X and Y dimensions. And all of these dimensions are being pushed to their limits in these latest technology nodes. So in this example, as you start scaling the CPP, the contacted poly pitch, or the pitch between transistors, the gate length goes down, but you start losing the fundamental characteristics of the transistor. The transistor is no longer transistor or a switch. It starts becoming a conductor, which doesn't become too useful for us for semiconductor technologies. The contact resistance also goes up. So another way of looking at this is taking a cross-section of the transistor in the X dimension. And what you see here is you see the contact, you see the spacers, the gate, which is where you have the transistor. All these dimensions are now atomically, with having a few atomic layers. So if you skip a beat, you end up having a shorter gate, or a gate length which is too small, or a contact which is too small for you to even get any signal in and out of the transistor. So the conventional device scaling is limited by these 3 parameters: the gate critical dimension, spacer thickness, and contact thickness. And all of these are being pushed to the limits for advanced transistors. Now, when we start looking at traditional lateral scaling, you see that when you start pushing these limits in, your off current starts going up. So you can get higher I effectives, but you start going higher in off current. And as you start lowering the CPP, your I effective at a constant VT ratio start going up. So you start having challenges in terms of maintaining performance at a narrow pitch. So now the industry has looked at other ways of doing this, and one way is to look at wide dimensional scaling. So trying to cram more transistors in wide dimension. So if you can't scale in the X direction, let's try to compress more and reduce the pitch of the metal lines. And what you see here, this chart on the right, is the line resistance as you start reducing the pitch of the lines. And the line resistance starts going up. It's the continuous reduction of these critical dimensions are causing exponentially higher line resistance. So that becomes a big problem for us to maintain performance. So again, all of this has been addressed by patterning techniques, materials, and integration innovations, and we have enjoyed that to date. But there's more now. Once you extinguish X and Y, you start getting desperate and start looking for these magic solutions. So these are what we call as hyperscaling elements. So for example, we start playing with the isolation, what we call as the double diffusion, single diffusion breaks. We start trying to get rid of those wasted spaces between transistors and get them closer together. We even have architectures where we completely remove the diffusion break, and now transistors are butted against each other and not interacting with them. We also are constantly looking at trying to reduce the track counts per cell. So how can we get functionality by reducing the overall tracks in the circuits? We also have new elements which are now being seen in the latest technologies, such as contact over active. In the past, you used to have contacts which have to be placed laterally across from the active regions. Now we have integration swizzles where you can actually have the contact right on top of the active fins, and you end up getting back area and hence a benefit towards your transistor architecture. So when we look at all of the innovations, and in this chart I'm showing starting from FinFETs, you see that we have steadily reduced the contacted poly pitch with all of these architectural but engineering innovations. And now we're at the point around 7 nanometer where it is very difficult to squeeze performance from a FinFET. We have made it as tall as we can. The fins start falling down. The pitches are also getting extremely tight. So what we have proposed in the earlier part of this decade was a stacked nanosheet transistor architecture, which you see here on the right. And we had also demonstrated early technology demonstration along with the 2 nanometer technology last year, where you can see we by stacking sheets on top of each other, you can now extend the performance of transistors and solution around the 2 nanometer, 3 nanometer technology do. So the industry has now adopted this quite widely, and we are seeing that we are moving from the FinFET era to the gate-all-around nanosheet era. And by this move in architecture, we start getting tremendous performance benefits for many years to come. So let's step into that a little more. When you look at FinFETs here on the left, the active channels are all vertical, and what we do is we rotate them 90 degrees, and now we have stacked sheets which are on top of each other. The channel is now physically disconnected, so these are truly gate-all-around architectures, unlike FinFETs. When we do a benchmark comparison of FinFETs versus nanosheets, the first thing which really sticks out is that by the fact that you can stack sheets on top of each other, you get a boost in the overall active area, which means you have higher current per transistor. You're also having the best electrostatics possible because it's a gate-all-around device. And by utilizing the latest lithography techniques like UV, you have fidelity in terms of defining multiple nanosheet widths and pitch. So the combination of gate-all-around and EUV are critical for moving from the FinFET to the stacked nanosheet era. Now, there are multiple innovations which are have been demonstrated and also which are being worked on right now for nanosheets. I'm showing some examples here. For example, on the left here, this is an example of what we call as bottom dielectric isolation. In addition to having these 3 channels on which are floating, we do have an active channel on the bottom, and we isolate that by adding dielectric to the bottom of the sheets, and that helps improve the off-current performance of transistors. So we are able to get a 10x improvement in off-current, and this ties into, again, the point which Jim made earlier. We need to innovate and generate the latest technology, which are high performing, but also having as low power consumption off current as possible to minimize power consumption in the off state. On the right here, this is an innovation in terms of inner spacers. And the reason I'm showing this is because over the multiple decades of the CMOS industry, we've been very good at patterning things top down. This technology requires you to now control the shape of this laterally. And you can see that by controlling this spacer dimension, you have much better control of the parasitics and the capacitance of the device. So there are a lot of unique innovations which come in with nanosheets, but also all of these innovations provide a higher attractive proposal in terms of performance and parasitics. Now, once you have the basic technology defined, you also need to have different types of sheet widths to accommodate for different transistors you need for technology. Like I said, using EUV, we are able to define multiple sheet widths. When you are talking about a transistor technology, you need to have multiple types of transistors, NFETs, PFETs, different types of threshold voltages. And this requires also a very novel type of gate stack scheme using high-k metal gate, but something which we call as voluminous gate stack technology. So in this technology, we basically use as minimal or no volume specifically for defining the threshold suites for the transistor. Now, once you see that in the overall roadmap, you can see that we have never stayed still for any technology generation. Starting from 90 nanometers, this chart, we have had key innovations which have come up in each of these roadmaps, from low-k dielectrics to SADP FinFETs to gate-around nanosheets with EUV. But the question is, if nanosheets can solution as around 3 nanometers, what is beyond that? I promised you 10 more years, so I'm going to try to give you that in the next few charts. So in order to do that, the question is, what is the next device and what is it really trying to solve? And we need to really ask ourselves this very tough question before we get into that, because any type of new device architecture is not cheap. It's not a simple decision. So we are convinced that in order to break the next barrier, we need to explore the Z dimension. And one example of that is IBM's vertical transport FETs, which we demonstrated and announced last year. There are multiple other transistor stacking and technologies out there by other companies and other consortia as well. But I'll be going over the details of this more in the chart to give it as an example of what can be expected in Z scaling. So as I said, when you look at the lateral cross-section transistor, you have the CGP or the CPP, which is the gate, the spacer, and the source drain dimensions. Any of these, once they are to the limits, start compromising the transistor's fundamental characteristics. And there is going to be a point in time in lateral scaling where we will not be able to scale any of these parameters. All of these will hit the limits, and touching any one of them is going to be disastrous. So the proposal for vertical transport FETs is to really break this paradigm, not have this equation dictate how a transistor is fit in a particular dimension. We do that by flipping this transistor over. And this slide here shows the flip-flop of transistor architectures over time. So we went from fins, which were straight up, to flat to make nanosheets. After a while, now we are saying that we're going to make it straight up again. But instead of having current going laterally, we're going to have current going vertically. And once you see this transistor and try to match up the source, drain, and gate, you'll understand that this architecture is no longer limited by the gate, contact, and spacer equation. You have broken this equation because the pitch is in this direction, You have your gate, which is vertically defined. The space is vertically defined, so you are no longer limited by that fundamental equation, which makes us cram these dimensions, these various transistor dimensions to the limits. So in order to build this device, you have to also now build this very differently because you're not building a lateral device. So this is built bottom up. We define the fins, and then we start building from the foundation, just like house is built. We start defining the source drain, the gates, and then the top contact. And this flow is used across the whole chip to demonstrate this technology. Now, once we build it, we have been doing benchmarking of lateral nanosheets, nanowires, both vertical and horizontal. And what we have found is that vertical nanosheets are indeed extremely superior in terms of performance, this is active power, compared to their lateral counterparts. We also see that when you compare resistance and capacitance, they provide an extreme benefit where you are able to get about 50% reduction in resistance and a 50% reduction in capacitance, both which help reduce overall power consumption. When we look at the operation of the transistor, the Vmax and Vmin are extremely important. By breaking the equation where we are now limited, no longer limited by pitch and spacer and gate dimensions, we're able to increase Vmax, and we're able to have a higher operating voltage and also not have any impact on Vmin, which improves our operating margin of the transistor. We also built ring oscillators. This was the true test to see if our capacitance was really as low as we predicted. And you can see that we had functional ring oscillators and also ring oscillator circuit capacitance, which was extracted to confirm that we are about 50% lower than our lateral counterparts. So overall, VTFET does provide some of these benefits which we are looking for. It provides higher density. It provides 50% reduction in capacitance resistance. It has the potential for lowering the energy. And also, we are having a higher operating margin, which is critical for high performance applications. This is just one example. Like I said, there are many other flows, both monolithic and sequential, which are looking at the Z dimension in terms of bonding. And any of these technologies are going to be the next future beyond lateral FETs. And we believe that this will provide a very robust pipeline for similar technology for years to come, well beyond 2 nanometers. So when you look at the overall transistor scaling roadmap, you can see that we are driven by transistor power and performance, and the architectural materials innovations have really sustained this engine and will continue that for years to come. Now, there is more in terms of the backend technology roadmap, because there's all I've talked about is on the transistor part of it. I'll quickly touch upon that in a few slides, where you can see here that in the backend side, where you're trying to wire up these transistors and build circuits, we have not stayed still as well. There's been innovation of innovation in terms of copper, in terms of low-K dielectrics, and UV lithography to get smaller feature sizes. But in order to sustain the growth for this semiconductor technology industry, the backend technologies have also been trying to look at scaling and X and Y dimensions. So one direct result of that is to shrink the overall metal pitch and critical dimensions. But it is bad for interconnect scaling. When you scale metal lines, they are no longer metals. So that's a well-known challenge in the industry. And here are some of the examples which have been considered or are under active research for various technology nodes to continue back-end extendability well beyond 2 nanometers. Beyond the basic line and dielectric research, there's also a paradigm shift from industry about power delivery. All circuits right now have signal and powers on top of the transistors. But what if we turn the transistor upside down and look in the Z direction for backend? And this is where backside power distribution comes in. So backside power distribution or BSPDN are technologies where you bring the power at ground below the circuit. You use the top of the circuit, the chip for signal routing. And by doing that, you now have more room to route your signals, and you're also able to efficiently deliver power to the transistors. So to sum it up, both transistor and interconnect scaling have a very robust future, well beyond 2 nanometers. Since there were many talks about chiplets, I do want to mention that that is a key part to add to this, because this is indeed leading edge, and not everything needs leading edge, or maybe a subset of the product would require leading edge. So in order to get the true benefit of technology scaling, you need to also have heterogeneous integration and chiplet technology on top of leading edge silicon technology to reap the benefits both in terms of performance and cost. So I'll end with the few comments I started off with. I believe the industry is definitely a solution for 2 nanometers and beyond. Vertical integration is key. It's used quite lightly in many places, but in semiconductor technology, vertical integration in terms of the transistor level, the cell block level, and the chip level, as I shown in the previous slide, will be the key for us to maximize performance, cost, and get the maximum for the technologies for years to come. Thank you.
Thank you, Hemanth. One question. Okay, so then I will ask a question. So we saw the cost increase, right? So when we go to VT-FET, what is the cost impact?
So as I said, when you use EUV, there is going to be a higher cost. But that's why I did not stop with the fact that VT-FET is the solution and we can go home. The leading edge technologies will always be expensive, and there'll be certain industries or certain customers who would want to use it for their applications. But with both backend and chiplet technologies, we will be able to soften that and open that up for many, many more companies. So, once you go to any leading edge technology, not only VT-FET, there will be a cost increase because you're going to use more expensive tools, lithography being one of them.
Thank you, Hemanth.